Hello there, dear students, and we are back again to keep explaining the uh, chapter uh, chapter 4 and the section 2. We reach this page. We are in this page now, page 85. We explain it. In here we have this table. This table is the specific heat for each of the substance. In here, look, we have specific heat capacity, for example, of aluminum or copper. Aluminum is which is equal to this number. Glass, this is the specific capacity of the glass, and so on. You have a lot of substance here, all of them. This table is not for memorizing. All of the teacher, they will give you this in exam actually, only for understanding this. And here we have a nice question. We have a device which is called calorimeter. What's calorimeter? Calorimeter, if you remember the previous video, we have explained the thermometer. Thermometer, it was one of the device for finding or measuring temperature. Calorimeter is the second device in here. This device is used for measuring specific capacity. In here, in this table, we have each of the substance, they have a different specific capacity. How the scientists they found this number, this value, specific capacity of each of the substance, how they found this value? By using this device, this calorimeter. So this calorimeter, let me show the device in here. This is the calorimeter device. This is the calorimeter device. This device are using for measuring specific capacity. But we have another parameter definition which is called calorimetry. Calorimetry, not calorimeter. Calorimeter is a device, but calorimetry, an experimental procedure using to measure energy transferring from one substance to another substance. In the previous section, we have explained what was transferring energy between two objects, and we said, for example, if you have two substance or two container, the first container and the second container. This container, for example, 10 CLZ, and the second container 2 CLZ. We know that both the object, both of the container, they have a different temperature. Because we have different temperature, it means in here there is a transferring energy among of them. Why, mister? Because we have different temperature. So even though we said transferring energy every time from the higher temperature to lower temperature, so that was 10 CLZ greater than 2 CLZ, so transferring energy, it must be from the left to right side. We have transferring energy from the left to right, from the greater temperature to the lowest temperature. So this is called the transferring energy as a heat between two containers. So this process, the name of this process, this is called calorimetry. Calorimetry. The process name is called calorimetry. The process name, experimental procedure is the process to measure energy transferring from one substance to another substance. Now we are going to solve exercise. Student Papa, look at me. Now, to solve example, we will apply this rule. In here we have two sides. The first side, energy absorbed by the water, and the other one, energy released by the substance. Let me again tell you on this in here. When we have two objects, for example, this one 25 CLZ and that one, for example, 10 CLZ, we have transferring energy from the higher temperature to lower temperature in that direction. I would like to ask you a question. Which of the container they get energy? They will absorb or they will receive so much energy? Of course, this container. Because the transferring energy from the left to right, and that object they will receive energy. So this one, it's called absorbing energy. Energy absorbed. This is called energy absorbed. So this is not important in here that which type of liquid you have. Is it mercury? Is it water? Is it oil? The type is not important. The important thing to determine, to mention, so which of the container will be absorber. So this absorb, energy absorb, but that one release or losting. We can say losting because they are giving this energy to the second object. They are losting. this object, it gives their own energy to the second container. This container are receiving. So with time, with time, the first object energy it become reduced and decreasing with time. So this is called losing energy, because they are losing their own energy because they are giving to the second object this container. So this is called releasing, or losing. This is called energy absorbing. So we apply both of them. The rule that we explained, Q energy, which this is the first side. You can write down in here losing energy, and in here absorbing energy, or vice versa. You can change the place. The place is not important. You can write in here absorbing losing. The important thing, one of the side releasing energy or losing energy, the other receiving energy or absorbing energy. So instead of Q, we are going to write down CPm delta T, and the rule that we studied in the previous section, the previous video, CPm delta T with CPm delta T. But this CPm delta T is for losing, but that CPm delta T for absorbing energy. To understand more, we are going to solve example now. Look, we have two sides. One of the side energy absorbed by the water, the other energy release. It means they are going to release their own energy with time. And for both of them, CPm delta T. Good. This example, it's solved and it takes time, but I'm leave this example now. I'm going to solve the first example. It's better. The first example and that one same thing. But this is important. I'd like to solve these questions. Question 1, page 87. So now look at me to solve together. First of all, the question said, what is the final temperature? But I forgot to tell you one thing, Baba. In this topic, every time you have two objects, maybe one of them water, the other oil. Maybe one of them, for example, any object, but the second maybe milk. Every time you have two objects, because every time you have transferring energy between two objects, you know this. We have two objects and there's transferring energy between of them. If the question said final temperature, it means TF. TF يعني final temperature. Final temperature, it means TF. Final temperature, for example, wherever you get any value, for example, the final temperature of this question is, for example, 25 Celsius. These 25 Celsius, it should be for both objects, because if you remember, I said if there's two objects, for example, transferring energy from 10 Celsius to 2 Celsius. After a few minutes, the first object, because they are giving their own energy to the right side, this temperature it become losing, right, with time. Maybe the first object, this one becomes 60 Celsius, and the right side maybe become 4 Celsius, and still it's keep transferring energy among of them. Maybe with time this 6 Celsius become 5 Celsius, and the right side still is become 5 Celsius. In that case, transfer energy will be stopped, because done. This is the last process, and this step is called thermal equilibrium. If you remember, I told you, from the beginning there is transfer energy, but the last step, when both of the objects they are reaching in the same temperature, this becomes thermal equilibrium. In that case, TF final temperature for both of them equal to 5 Celsius. This is final temperature and this is still final temperature, because you know why for both of them it's same? Because both of them they have same temperature, and that's why this temperature, final temperature, is for both of them, because both of the containers they have same temperature, they have identical temperature, so for both of them the final temperature is equal. Okay, so now we are going to solve example. The first example. Good. Question 1. What is the final temperature? What is the final temperature? But okay. Question 1. Find the final temperature when 3 kilogram gold, this is the mass of gold, mass 3 kilogram of gold, 3 kilogram of gold mass, at 99 Celsius, drop it into 0.22. So at 99 Celsius, this temperature is become the initial temperature, the first temperature. How we know, mister? Because in here the question they say find final temperature. Of course, that one becomes initial, the first temperature. So Ti become 99 Celsius. And is dropped into 0.22 kilogram of water. So this is the mass of the water. Mass of the water 0.22 kilogram, and the temperature of the water in here we have 25 Celsius. Ti 25 Celsius. So now we have in here the mass of the gold 3 kilogram and the mass of the water 0.22 kilogram, and the first temperature of the gold 99 Celsius, but the second temperature of the water 25 Celsius. In here, so look how we can solve this example, Baba. Look at me. Look. This is for the water. Okay. In here, first step, we have to find which one of them is become absorbing, which one of them become releasing or losing energy. Could you tell me the direction of transfer energy? We said every time direction of transfer energy from the higher temperature to lower temperature. Yeah, from that direction, left to right, right? Because it's 99 Celsius and that one 25 Celsius. From the left to right, transferring energy from the higher temperature to lower temperature. Okay. So this is water, and the water, they are receiving energy, and the water become absorbing energy, but the gold, they are losing their energy. Why they are losing energy, mister? Because they are giving their own energy to the waters. That's why. Yalla. Apply the rule immediately. The first one, CPM delta T, this is for gold, yani for losing, equal again CPM delta T, this for water absorb. Good. But in here, if you remember the table that I told you, CP of gold is specific capacity of the gold. Me as a teacher, I don't know the value actually, but I will give you in exam. I'm going to give you the value of specific capacity for each of them substance. So in here, for the value of gold, which is equal to, I think, gold 129. The value CP of the gold 129. So instead of CP of the gold, write down 129. Multiply the mass. The mass of the gold in here we have, look, 3 kilogram. The mass of the gold 3 kilogram times. Look, I forgot to tell you one thing. If one of the substance, for example, absorbing, if we have absorbing, we have to say TF minus TI. But if we have losting, we have to write down TI minus TF. But because in here we have gold, and gold is losting, so instead of writing delta T, we are going to write TI minus TF. Okay, TI minus TF. I'm going to repeat again. CP 129 times, this is the mass of the gold, this is specific capacity of the gold, and this is the mass of the gold. And instead of delta T, how do we know that? Do we have to write down TF minus TI or TI minus TF? Because in here, this part is losting, because losting, write down TI minus TF. But the right side in here that you have, CP of the water, every time the CP of the water, the number is equal to 4186 times. What was the mass? The mass of the water in here we have 0.22 times. And delta T, and instead of delta T in here, we can write down TF minus TI because the water is absorbing. So instead of delta T, if we have absorbing, write down TF minus TI. But if we have lost T, write down TI minus TF. So 4186 times 0.22 times, we have to write down, find this TF, right? We have to find this TF minus. And the TI of the water, it was 25. What about in here? 129 times 3. TI of the gold, it was 99 minus TF. So in here we have to arrange this equation to find this TF. To find this TF, students, then I arranged the equation now. So as we said now, the left or right side, one of the side must be water and the other will be gold, and water absorbed with gold released. So Cp of the water 4186 times the mass of the water, it was 0.22, and instead of delta T, because in here we have absorbing, we have to write down TF minus TI. Okay, then the right side in here we have gold. Gold, it's releasing. So instead of Cp of the gold, we have to write down 129. The Cp of each of the substance will give you an exam, no worry. So instead of the mass of the gold, it was 3. And because in here we have a releasing, so instead of delta T, you have to write down Ti minus Tf. So the Ti, the first temperature of the gold, it was 99 minus Tf. So our purpose in here, you have to find the Tf, final temperature. Look. First of all, multiply this number together. 4,106 times 0.22. The answer 9292. And copy the bracket again. TF and the first temperature of the water, I forget, it was 25. Good. Equal. And 129 times 3. 129 times 3. The answer 387. And copy the bracket again. 99 minus TF. So then we have to we have an easy technique. You can divide both sides by this number, 920, to find the answer easily, not like that, multiply one by one inside the bracket, because actually this is take time. Both of them will try the technique, but maybe this take time. So divide both sides by this number, 9 to, and this number will be cancelled. On this bracket it's left TF minus 25 equal. Then divide these two numbers, 387 divided by 920.92. 387 divided by 9. The answer 0.42. Bring down this bracket to 99 minus TF. Then, because next to bracket this number is left, this is obligatory actually. You have to multiply this for both of them inside the bracket. 0.400 times this number multiplied by 99. The answer will be 41.6 minus this number times TF will be the same thing. TF. Bring down this again. Then we have to arrange this equation. A letter in a side and a number in another side. A letter in a side, a number in another side. Bring it down this TF. Take this number to the left side with the letter. It will be positive because it's negative. When you are taking to the left side, you have to change the sign. It will be positive 0.42 TF equal. And copy this number bring down again 41.6 and take this negative 25 to the right side. Will be positive 25. 41.6 plus 25. The answer will be, let me write down here. The answer of the right side will be 66.6. and the answer on the left side. How we can plus this both of them? In here we have TF, but in here there is no number, it means 1. So 1 plus 0.42 will be 1.42 TF. 1.42 TF. So actually finally we are close to finish. How we can find TF? Divide both sides by 1.42, 1.42. So 1.42 will be cancelled. 66.6 divided by 1.42. The answer will be 46.9 or 47. TF, the final temperature, 47 Celsius. This is the last answer. It's about the question 1. Question 2 in here. Let me solve even though question 2. Question 2. As at 25, 0.25, we have look, 0.25 sample of this object initially. This is the sample of this object. This is the mass of this object. The mass 0.225 kilogram, and initially, and this is the first temperature Ti, which is equal to 97.5 Celsius, and it's dropped into 0.115 kilogram of water, and this is the second object. And as I told you, this question is between two objects. One of them is water, the other another object. Sometimes milk, sometimes water, sometimes milk and water, or water and cup. This topic is between two objects because you have transfer energy. That's why. So this is the mass of the water. The mass of the water 0.11 kilogram. And initially temperature, this is the first temperature initially, Ti, which is equal to 10 Celsius. If the specific heat capacity of this object they gave us, it's okay, good. What is the final equilibrium temperature? Final equilibrium temperature, يعني find TF. Find TF. Find the final temperature. Find TF. Good. And as I told you, final temperature, يعني the temperature for both of the object. Look, we have two objects, this object and water, and the mass for each one of them, and the first temperature for each one of them. The question said find final temperature, يعني the final temperature or equilibrium temperature. It means the final temperature for both of them. So again, first of all, in that case, we have to determine which one of them is absorbing actually. Again, we have now transfer energy from the left to right, because this is the greatest temperature and this is the lowest one. So transfer energy from the left to right. Again, the water, they are receiving energy. So the water become absorbing, but this object become losing. The water become absorbing and that one become losing. Because the water is absorbing, يعني delta T, it must be Tf minus Ti. But this object is losing, the delta T, it must be Ti minus Tf. Good. يلا. Write down the same rule again. Cp m delta T is for the object, and the other one for the water, Cpm delta T for water. And we know that the water, it was absorbing, and that one is released. Good. The Cp of this object, the question they gave us, it was 230 times. What was the mass of the object? The mass, it was 0.225. 0.225 times delta T, because this object, they are losing their energy, يعني delta T become Ti minus Tf equal. The right side in here we have waters, so the water is absorbing, so the delta T must be Tf minus Ti. But the first one, the specific capacity of the water, we know 4,186 times, and the mass of the water, it was 10 Celsius. No, the mass of the water, sorry, it was 0.115 times, and the delta T, it must be Tf minus Ti because the water is absorbing. Let me rearrange this equation. Yeah, first of all, multiply these two numbers. 230 times 0.225. The answer is 51.75. Bring down this bracket. What was the value of the initial temperature of this object at Ti? Ti, it was 97.5. So instead of Ti, write down 97.5. So Tf is the unknown value. You have to find Tf. Bring down again Tf equal. Yalla, we have to rearrange the right side too. Multiply these two numbers. 4,806 times 0.115. The answer 481.39 times, bring down Tf minus, and what was the initial temperature of water Ti? Ti, it was 10 Celsius. Good. Then do the same thing, the same technique I told you. Multiply both sides by this number. 51.75. So these two numbers, both of them going to be cancelled. So bring down this bracket. 97.5 minus Tf equal, divide both this number. 481 divided by this. 48139. 39 divided by 51.75. The answer 9.30. So, and do not forget this bracket. Most of the students, they forget this bracket. Bring down this bracket. Tf minus 10. Then you have to arrange the question again. 9.30 times Tf will be 9.30 Tf, and 9.30 times 10 will be 93 only. And bring down this number to 97.5 minus Tf. Then rearrange the question, letter in a side and number in another side. So bring down the 97.5, then take this negative 93 to the left side, will be positive 93 equal, and bring down this letter with the number 9.30 Tf, and take this negative Tf to the right side, will be positive Tf. Plus this number together, 93 plus and 97.5. The answer will be 190.5 equal, and 9.3 with 1 will be 10.3 Tf. So to find Tf, finally divide both sides by 10.3. Let me write down here because there is no place. 190.5 equal to 10.3 Tf. Divide both sides by 10.3 and 10.3. This 10.3 going to be cancelled. I'll divide this both of them. 190.5 divided by 10.3. The answer will be 18.4. That last temperature Tf, which is equal to 18.4 Celsius. Oh, this is about question 2. Question 3. Okay. Question 3. I think question 3 is different. Question 3. So actually, I think it's better to solve question 3 by yourself, because question 3 is same thing like question 1 and question 2. Find again, what is the final temperature? Again, find the value or the final temperature. Same thing, do the same process. I'd like to solve question 4 because question 4 is different. Question 4, different question in here, different idea. Good. Question 4, look, focus with me. Question 4 said a cup, and here again you have two objects. The first object is cup. It's made on an experimental material that can hold hot liquid. The 0.75 kilogram cup. So this is the mass of the cup. The mass, it was 0.75 kilogram. Has the initial temperature. So the TI of the cup 36.5 Celsius. When it's submerged, the cup, it's immersed, it's sink, it goes under the water, and the mass of the water. So the two objects in here, now we have the first one cup and the second one water. Okay, the water's mass was 1.25 kilogram, and with the initial temperature of the water 20 Celsius. And what is the cup specific capacity? What is the cup specific capacity? Find the specific capacity of the cup object. Okay, if final temperature is 24.4, this is really important. But Mr. in here we have two objects. Final temperature for which one of them? For cup or water? I told you every time in this topic, final temperature, and the value for both of them, because I showed you before, because as the last procedure, the last process, both of them, they will reach the thermal equilibrium, and their temperature for both of them becomes same. That's why this temperature 24.4 and 24.4 Celsius, this temperature for both of them, because at the end both of them, they will reach at the equilibrium state. So the final temperature every time for both of them, same thing. Good. So easy now. We have to find the CP of the cup, and we know the CP of the water 4186. So I think it's clear. Now in this, the things that in here we have is different. And instead of finding final temperature, no, in here we have final temperature, but we have to find now, and instead of final temperature, we are going to find now specific capacity of the cup. Good. Yeah. CP m delta T equal to CP m delta T. One of them cup and the other it was water. But I forgot to tell you which one of them absorbing, which one of them is lasting. The temperature of the cup, it was the temperature of the cup, it was 36.5. Cup 36.5 cup. But the water, the temperature of the water, I think 20. Yes, 20. So again, Yalla, tell me which one of them absorbing, which one of them losing. We have transferring energy from the left to right. The water again absorbing because they are they will receive temperature, but the cup they are losing because they are giving their own temperature, their own energy to the water. So cup become losing or releasing temperature. So again, the water become absorbing. Good. The cup releasing. Yalla, CP, we need to find CP. We have to find now CP. We have to write down or find. We are going to find specific capacity of the cup times. What was the mass of the cup? The mass of the cup, it was 0.75. 0.75 times, because the cup again losing, so instead of delta T you have to write down Ti minus Tf, not Tf minus Tf, Ti, because in here we have losing, the cup is losing again, losing every time Ti minus Tf. But the right side you have water absorbing, Cp of the water every time 4186 times the mass of the water 1.25 times, and instead of delta T you are going to write down Tf minus Ti, because water it becomes absorbing. Yalla, only have to write, you have to arrange this formula equation. Bring down Cp times 0.75 times, so inside the bracket you have Ti minus Tf. So the Ti of the cup, it was 36.5, and 36.5. The TF for both of them, it was 24.4. So 36.5 for the cup. Good. On the right side, 4186 times 1.25. TF, it was again 24.4 minus, but the initial temperature, TI of the water, it was 20. Finish. We are done to put all of the number for each of the place. Only in here we have to rearrange the equation. First of all, bring down the CP times 36.5 minus 24.4. 36.5 minus 24.4 equal to 12.1, and 12.1 multiplied by 0.75, 0.75, the answer 9.075 equal. The left side actually done. The right side is left. To arrange it, multiply this together, both of them. 4186 times 1.25, the answer 5. Or wait, not this. Wait a minute. It's better to multiply inside the bracket first. 24.4 minus 20. 24.4 minus 20. The answer 4.4. Now this result multiply for both of them by both of them. Times 4186 and times 1.25. So the answer for all of them for all of them of the right side become 23,023. This is the answer, the result of the right side, because all of them is number. First I minus this two number, then the result of this bracket, the result you should multiply for all of the number in here that we have. Okay, then it's so easy. How to find CP? Divide both sides by 9.075 and 9.075. So these two numbers are going to be cancelled, and CP, which is equal to divide this number together, divided by 9.075. The answer will be 2536.96. This is the specific capacity result. But what was the unit of specific capacity? Please don't forget for the exam. The unit of specific capacity, we said joule over kilogram with Celsius. And this is the answer of question 4. Okay. Question 5, same thing. Again, you should write down. You have to find the specific heat capacity. The specific capacity for one of the substance. But let me solve this for you too. It's okay to understand more. Question 5. A brass is an alloy made from the copper and zinc. So the two objects in here that you have, one of them copper and the other zinc. 0.59 kilogram brass. Brass, it means the copper. Okay. A brass, it's made from the copper and zinc. So this is the structure. This is the structure of the brass. So in here we have two objects. One of them brass and the other water. So the object in here that you have, brass and water. Copper and zinc is the structure that is made of brass. Brass, it's made from the copper and zinc. Okay. But the two objects in here, one of them brass, the other water. So 0.59 kilogram brass. This is the mass of the brass, 0.59 kilogram. Okay, and 98 Celsius is the initial temperature of the brass, 98 Ti, 98 Celsius. Drop it into 2.80 kilogram of water. So this is the mass of the water, 2.80 kilogram of water at 5 Celsius. The first temperature, Ti, 5 Celsius. If the equilibrium temperature is 6.8, equilibrium temperature, equilibrium temperature. The equilibrium temperature, it means final temperature, TF. Because equilibrium temperature, I told you, this final temperature, it must be for both of them. So, TF for both of them 6.8 Celsius and 6.8 Celsius, because the question said final temperature or equilibrium temperature. Equilibrium temperature, we have studied. It means the temperature for both of them, it must be same. That's why for both of them, we wrote down 6.8, 6.8. And the question said, what is the specific heat capacity of the brush? So find specific heat capacity of the brush. This specific capacity of the brush is equal to what? We know specific capacity of the water 4,186. And write down here if there is a place. Okay. Yalla. Let me do it in here. CPM delta T, which is equal to CPM delta T. First of all, which one of them is absorbing and losing? It's clear again. We have transfer energy from the left to right. The water again absorbing, the brass losing. The left side, let me say, consider the left side, they become brass, and the right side water. We have to find the CP of the brass, bring down CP times, and the mass of the brass, in here we have 0.59 times, and delta T, because the brass it's losing energy, so instead of delta T, write down Ti minus Tf equal. What about the right side? The right side is about water and absorbing. CP of the water in here, we have 4,186 times, and the mass of the water 2.80 times. And instead of delta T, you have to write down Tf minus Ti. Only you have to arrange the question now. Bring down the Cp times. So Ti of the brass in here 98 Ti, and the Tf is 6.8. If we put these two numbers in here, become 98 minus 6.8, right? 98 minus 6.8. So immediately I would like to minus it because we don't have place. 98 minus 6.8, 98 minus 6.8 will be 91.2. 91.2 multiplied by 0.59, multiplied by 0.59. The answer will be 53.8. 53.8. You see the answer of the left side. And only Cp times 53.8 is left for the left side. Equal. What about right side? For 4,000, or leave this now. Tf minus Ti. Tf, we said Tf 6.8 for both of them because same number 6.8 minus Ti of the water, it was 5. So 6.8 minus 5, 6.8 minus 5, the answer 1.8. So 1.8 times 2.80 times 2.80 and times 4,186. The answer will be on the right side value 21097.44. Then what is left? Cp times 53.8 equal to 2109744. How we can get the value of Cp? Divide both sides by 53.8 and 53.8. This will be cancelled. So divide both this number divided by 53.8. So the answer will be Cp of the brass that in here we found, which is equal to 392. And the unit of Cp specific capacity, we know joule over kilogram Celsius. The answer is Cp 392. And this is the answer of question 5. Good. The other question you can solve by yourself. It's the same thing and it's too much. That's why it takes so many times. You can solve by yourself actually. We have solved a lot of examples. I hope to get the benefit, and it was so easy actually, I think. In here now, another part is left, which is called latent heat. What is latent heat? Latent heat, in general, leave this page now, later we will explain, but we have some definition. First, let me tell you what is latent heat. Latent heat if you focus in here with the definition said, energy, the energy per unit the energy per unit mass that is transferred during phase change of a substance. Latent heat, energy per unit mass. So in here we can understand more by knowing the rule. If you remember in physics, I told you, first of all, look at the rule, you can understand everything. So latent heat rule look at me, just look at this whiteboard. Latent heat Q, which is equal to ml. What is the meaning of Q? Q, we studied in the previous section. Q, it was energy or heat. Heat or energy transferred. M is the mass, which is equal to mass. L, this is our topic. L is called, the name of this L, which is called latent heat. Latent heat. According to this rule, if you can now go to find the value of latent heat, Q equal to ml. How we can find latent heat L? Divide both sides by m by m. This m going to be cancelled, so only L is left, only this L latent heat is left, which is equal to Q over m. Q over m. Now in here we found latent heat. So latent heat equal to what? Equal to the relationship between transferring energy Q per unit mass. Energy per unit mass. That's why the definition now it said energy per unit mass. Energy per unit mass. Energy per unit mass. That look by only understand the rule, you can understand even the what's latent heat. So we have a mass of any object, and we will give energy. For example, we have this container, and the mass of this container 25 kilogram, and give this mass or this container energy. For example, the energy, any of the energy, give this object energy. After a while, if the state of this phase, the state of the matter, for example, if it's solid, if this is solid, for example, when you are given this object heat, after a few seconds, or after maybe it takes 1 hour, after a while, we see that the state of the matter become changed. Maybe it become liquid. So this is called latent heat. We have a container, we have a mass, and we are giving heat to this mass. We will give heat to this of the object of this mass. After a few seconds, the state of the matter as solid become liquid during changing of the phase. If we have a containers, and the mass of the container, which is equal to any of the numbers, and give this object energy, after a while the state of this matter become changed. So this process is called latent heat. Energy per unit mass, yani give the energy to this object, and this object they have mass, so this relationship is called latent heat. What is the unit of latent heat? Let me find in here, according to this rule, the unit of heat, we know this is joule, over the unit of mass, kilogram. So the unit of latent heat become joule over kilogram, according to this rule, joule over kilogram. So in here we have two type of latent heat. The first type of latent heat, let me write down the rule again in front of you. L equal to Q over M. We have two type of latent heat. The first type of latent heat, which is called heat of fusion. Heat. If we have heat of fusion, instead of Q, write down F. F, it means energy of fusion. Energy that in here we have transferring. This is called energy or heat of fusion. Or not in here is better. Write down in here, next to the L letter, latent heat of what? Fusion. Latent of fusion. Again, the definitions will be the same thing. Again, energy per unit mass. But in here, because we have fusion, what is the latent heat of fusion? Here we will say latent heat of fusion. Let me show you. Look, latent heat of fusion. Again, energy per unit mass. Again, I told you energy per unit mass, but transferring to change a substance from solid, from solid to liquid or liquid to solid. يعني we have the first type of latent heat in here. We have heat of fusion, LF. In LF type of the latent heat, we have only transferring energy between liquid to solid or liquid solid to liquid. يعني for example, when you have when you have this object, for example, this object state is solid, and after it's become liquid. How it's become liquid? How? When we are giving them energy, of course. And the mass of this solid, for example, the mass of this container, this state of matter solid, for example, 10 kilogram, let me say. So when you have this container, this state of solid, giving this solid Q energy, and the mass of the solid 10 kilogram, after a while the state of the matter become changed to solid. So converting solid to liquid or vice versa, liquid to solid, this process called latent heat of fusion. Latent, يعني when you are giving heat energy to any of the object, while you are giving energy to the object, if the object state become changed from liquid to solid or solid to liquid, this state called heat of fusion. But the second type in here, we have heat of vaporization, LV. Heat of vaporization, LV. Same thing again, energy per unit. Again, energy per unit mass. The same thing. Again, LV, which is equal to Q over mass. Same rule. Again, we are giving the object energy per specific mass, per unit mass. But while you are giving the object energy, if the object state of matter become changed from liquid to vapor or vapor to liquid, this is called heat of vaporization. So we have two type of heat. We have two type of latent heat: heat of fusion and heat of vaporization. In heat of fusion, you are giving the object heat, and the object state become changed from liquid to solid or solid to liquid. This is called heat of fusion. Done. But when you are giving object again heat, but the changing state of the matter, if from liquid to vapor or vapor to liquid, is called heat of fusion. And both of them are a type. Both of them are a type of latent heat. Both of them type of latent heat. If you notice that for both of definition, they have same meaning: energy per unit mass. Look, energy per unit mass, energy per unit mass. All of them same. Good. So now we explain it, and even though I told you the unit of latent heat, look, joule per kilogram. Why? Because latent heat, which is equal to Q over mass, the unit of Q energy joule and the unit of mass kilogram. So that's why the unit of latent heat become joule over kilogram. Now we understood what's the meaning of latent heat and their types. We have this table, this graph, actually important to understand each of the part. In each of the part in here, first let me tell you, Baba, the horizontal axis, this is called heat. The vertical axis, this is called temperature. What is the meaning of this? It means in the horizontal axis, we have a transferring energy, but in the vertical we have temperature. So be with me to understand what is this and what's the meaning of each of the part. Look, in part A, if you notice that in here, we have part A, in this region in part A, the temperature, I told you the vertical line is the temperature. The temperature is between 0 and negative 25. Negative 25, you know that, I think. At 0 Celsius, يعني that this object, the state of the object is freezing, so cold if we have 0 Celsius. But in here, even though we have below zero, below zero have negative 25. يعني this is ice. That's why it's ice. I mentioned for you, this is ice region. The state of the matter, it's solid, ice, freezing, because we have negative 25 Celsius. The range between 0 and negative 25 Celsius. This is about range A, part A, between 0 and negative 25 Celsius. 0 to negative 25 Celsius, the state of the matter in here, solid, and ice, we can't say freezing because negative 25 is the temperature is below 0. Then what we are going to do? What are we going to do now? What we are going to do now? Look, we are going to give this region A. Here we have ice. We are going to give this region A ice energy. We are going to give them energy. When we are going to give them energy, if you notice that in here, if you notice that, with me, look, when we are give this object, this part A ice energy, we see that the temperature of the ice is going to be increased. It goes to up. Why it goes to up? Because we give them energy. First it was negative 25 Celsius, so cold, right? We get negative 25 Celsius, but because it's cold, I give this negative 25 Celsius energy, and they are receiving energy. The temperature of this become increased until it reaches to the 0 Celsius. So in part A, we are giving heat energy as a heat energy to the ice state. The energy, the temperature of this ice state going to be increased until it reaches to the 0 Celsius. This is part A. In part B in here, if you notice that in part B we have ice plus water. In part B in here, and look, who knows what is the temperature of part B? Look, if you notice the temperature of the part B is 0 Celsius. 0 Celsius. In this region, the temperature is 0 Celsius. The temperature 0 Celsius. In here we have ice plus water. Why ice plus water, mister? Because first it was negative 25 Celsius, but we gave them energy, and the energy going to be increase until it reached to the 0 Celsius. So in here, sorry, half of them ice, half of them water. But part A, it was totally freezing, negative 25 Celsius. But we give them energy, then until the temperature becomes 0 Celsius. So the part B, half water, half ice. Then in part B, the temperature of part B still is 0 Celsius. Look, 0 Celsius. Then we will decide again to give more energy, to give them more energy. In part B, we know in part B the temperature is 0 Celsius. But I would like to give more energy to this region. When we are give them more heat, more energy, what do you expect to be happen? In here, look, give them more energy. Give them more energy. We see that the temperature of part B, the temperature in here, half water, half ice. When we are giving them more energy, we see that the temperature again, it keeps increasing. Look, it keeps going to up. It goes up. Why? Because the temperature in part B, it was 0 Celsius. temperature. In part B, it was 0 Celsius. But in that point, I decided to give them again more energy. When we are giving more energy, the temperature of the part B is going to be increase until the temperature of part C is going to be increased. When we are giving them energy, the temperature going to be increase. In this region, only water is left. Only water is left. First, it was ice freezing. It was negative 25 Celsius. We gave them energy. The temperature, it was increased until it reached to the region B. It was half water and ice. In this point, again, we decide to give them more energy, and the temperature going to be increased more. So in this region, only water is left without ice, because when they are receiving energy, it become melting. Of course, they are receiving energy. The steps and the state of the matter is it's going to be changed and becomes melting. So only in the part C, only water is left until the temperature it reaches to the 100 Celsius. Look, the temperature it reaches to the 100 Celsius. In 100 Celsius, in that point, what is the meaning of that point? But first, let me tell you part C region. From 0 to 100, from 0 to 100 in this region, the water's temperature increases. The temperature of the water increases. And ice begin to melt until ice begin to melt and change into 0 Celsius. In here, the ice totally and become melting, and because on here only water is left, ice begin to melt. So the ice it's begin to melt and change water's temperature to and change into waters at 0 Celsius. So the temperature of the ice become changed and become melting. So this region is important because the water's temperature is going to be increased, and even though the state of the matter in here is liquid, only water. At part D, in here, at 100 Celsius, this 100 Celsius is called boiling point. At 100 Celsius, the temperature stops increasing and the waters turn into steam. In here, when you have a glass of the water, you are giving them more energy. They are receiving energy. First you have ice, then after ice you have water. After water it become boiling, become steam. But in here, not totally steam. Half of them water, half of them steam. And the temperature stops in here. Look, only the water turn into steam. The water's phase becomes steam. But in this point, I want to give this water and steam more energy. If you notice that in the last region, water has completely vaporized. In here, we are going to give them more energy, and the temperature of the water and steam going to be increased. So in here, if you notice that only steam is left. So the temperature of the steam going to be increased. So in this region, water has completely vaporized. Let me repeat again all of this part. In here, first it was only ice, and the temperature it was negative 25 Celsius, freezing, cool. We give them energy, and the temperature going to be increased until it reaches to this Celsius, until it becomes 0 Celsius. Ice begin to melt and change into water as 0 Celsius. At first it was freezing, negative 25 Celsius, but we are giving energy. The temperature going to be increased until it reaches to the 0 Celsius in here. What about part B? In part B, half ice and half of the water, because the temperature become increased. Half of them ice, half of them water. In this point, the temperature of water going to be increased. When the temperature of water going to be increased, in here only water is left. So from 0 to 100, from the 0 till 100, from 0 till 100, the water temperature going to be increased. Going to be increased the water temperature. So in here only water is left without ice. After water, if you give the water more energy, of course after waters become steam. but not totally steam. Half of water and half of steam. In here, look, the light goes up because the temperature is going to be increased when you are giving the water steam or energy. Of course, the last region totally will be steam, or totally vaporized. This is the idea. And here, it explains the same thing now I told you. You can read it by yourself later. Even though in here too, in part A, look, in part A, in here the temperature become increased. Same thing. The temperature of ice increases. Same thing actually. But in here we have to. I have to tell you something important because we need it for solving example. Look, Baba, if we have difference in temperature, we have to use this rule, CPM delta T. Okay, because in here we have two temperature, first temperature and second temperature. In here we have to apply CPM delta T. But if we have 0 Celsius, 0 Celsius, 0 Celsius يعني what? In 0 Celsius, the state of the matter is solid. 0 يعني freezing, solid. And because this is solid, the definition of heat of fusion we said, converting state of the matter from solid to liquid or liquid to solid, liquid to solid. Because you have 0 Celsius, the rule you have to write down QMLF, heat of fusion. Because you have 0 Celsius and 0 Celsius it's solid, that's why. Yeah. And the second one here again you have different temperature every time use this rule CPM delta T. But in here we have 100 Celsius. 100 Celsius 100 Celsius, 100 Celsius, we are going to be write down MLV, vaporization. Why vaporization? Because the definition of the vaporization said converting the state of the matter from liquid to vapor or vapor to liquid. 100 Celsius is vaporization step. That's why. Let me show you again. Definition. Wait a minute, where's the definition? Look, heat of vaporization changes substance from liquid to vapor or vapor to liquid. But that's why, because 100 Celsius, because 100 Celsius is a vaporization step, boiling step. That's why you have to write down MLV. But in heat of fusion, if we have 0 Celsius, write down MLF. You know why MLF? Because at that temperature, 0 Celsius, the state of the matter is solid. That's why. The state of the matter is solid. And because in here they said solid to liquid, liquid to solid, write down MLF. But if you have vaporization 100 Celsius, write down MLV. And this is not important before to solve example. And actually, I think I told you all of the things. Let me check. I didn't forget anything. Done. In here we have another definition of phase change. Phase change is the physical change of a substance from one state, and you want to convert state of the matter from solid. If you want to convert state of the matter from solid to liquid, then to gas. This is called phase change, a physical change of the substance from one state to another, either from solid to liquid or either from liquid to gas. So this is called phase change. Okay. Now I think before to solve exercise, this one is the latent heat, fusion and vaporization for each other substance. Again, like the specific capacity, as I told you, we will give you an exam, no more, inshallah. Now we are going to start to solve example. Okay. Solving example now, or leave this question inshallah for the next video. We will explain this page. We reach in this page to solve latent heat questions. Thank you for all, and I hope to understand the topic and have a nice day.